So hello everyone, welcome to the channel. So in this video I'm going to show you the river turbidity mapping using Sentinel-2A Imagery in Google Colab. So now let's get started. So monitoring a river turbidity is essential for understanding the water quality, ecosystem health and sediment dynamics and the impacts of human activities on aquatic system. So traditionally the turbidity has been measured through a field sampling, which although accurate is a time consuming and spatially limited and difficulty to conduct frequently. So with the rapid advancement of satellite earth observation technologies, so the remote sensing provides a reliable and efficient approach to estimate the turbidity across a large spatial extent and over a long period. So here we're going to use the Sentinel-2A Imagery launched by European Space Agency under the Copernicus program, offers a multispectral imagery with 10 to 20 meter resolution and a revisit of frequency of 5 days, making it highly suitable for monitoring the surface water system. Several spectral indices derived from the Sentinel-2 reflectance data, such as the Normalized Difference Turbidity Index and Normalized Difference Water Index, enables precision identification of water bodies and estimation of sediment concentration. Because the turbidity typically increases with the suspended sediment, the NDTI serves as an effective proxy for turbidity estimation, especially in river and dynamic water environment. So the analysis begin by installing the essential packages and authenticating the Google Earth Engine within Google Colab. We're going to generate an interactive map interface used to manually select the study area. And next we're going to import the Sentinel-2A Imagery, and it's going to be linked with the Sentinel-2 cloud probability dataset to enable the cloud masking and custom functions to generate NDWI for water masking and applying the cloud filtering and compute NDTI for each Sentinel-2A scene. And we're going to generate a monthly turbidity composites are created using X-rays resampling function, producing a monthly maximum NDTI value to capture the peak sediment and turbidity events. So the analysis also generate a panel of monthly maps and a continuous time series plot representing the monthly mean turbidity level. Finally, the results we're going to export it as a high resolution JPEG image and we're going to download it, and we're going to download the CSV file summarizing the monthly turbidity and making the output suitable for our scientific reporting and decision makings. So now let me get back to Google Colab. So in our first step, we're going to install the XE package here. So to do that, I'm going to mention install and I'm going to give it some space here, and I'm going to mention quite and XE. So once you did that, we're going to navigate to this option called run cell. So I'm going to click this option. So it's currently loading it. So it's going to download all the required package here. So let me remove this, and let me rerun this. So now it's going to download the packages here, so I can able to see that. So now we managed to install some required package. So the next step, I'm going to navigate here, and I'm going to click this option called code. And the next step, so I'm going to import the Google Earth Engine Python client library. So to do that, I'm going to mention import and GEE. Similarly, I'm going to import the geemap wrapper to display the interactive maps here. So similarly, I'm going to mention import, and I'm going to mention geemap. And the next step, I'm going to import the X-ray, a library for labeled multidimensional array. So it's great for time, latitude, longitude data. So to import that, I'm going to mention import, and I'm going to mention X-ray as XR. And the next step, I'm going to import XEE. So I'm going to mention import XEE, and this particular one is used to convert the server side image collection into a local X array dataset for plotting and analysis. So let me run this. So I'm going to click this option. So it's going to install the required packages here. So now the code has ran. So in the next step, So in the next step, we're going to authenticate and initialize the Google Earth Engine. So to do that, I'm going to click this option here. So basically, this particular step is very essential. Without authentication and initialization, so you cannot access the Earth Engine data or the runs server side operations. So to do that, I'm going to mention is Earth Engine dot authenticate. So here you can able to see it's automatically it's came here. So I'm gonna click accept. I'm gonna enter as tab. So it automatically came as an authenticate. And similarly, in the next step, I'm gonna mention as initialize. So I'm gonna mention Earth Engine dot. So it automatically pop up here. So I'm gonna click this option called initialize, and so inside this initialize function, I'm gonna mention as a project equal. So basically, I'm going to copy and paste my Earth Engine project ID. So let me show you that. So this is my Earth Engine code editor. So in that, I'm going to navigate to this option, and I'm going to click this option called project info. And here, I'm going to copy this particular one called the cloud project, that is Earth Engine Terraspatial E2A2U. So we're going to copy it, and let me navigate to my Google Colab, and I'm going to paste it inside here, Control V. And the next step, I'm going to add a comma here, and here I'm going to mention the option URL equals to, and they're going to mention a single quote here, and I'm going to copy and paste this particular so this particular one is important because it is useful when used to you expect a larger data transfer from Earth Engine. So for that, I've mentioned this option URL here. And now let me run this. So I'm going to navigate and click this option. So now a window pop-up saying allow this notebook to access your Google credentials. So this allows the code executed in this notebook to access your Google Drive and Google Cloud data. Review the code in this notebook prior to allowing access. So click this option called allow, and it's going to pop up here, and I'm going to select my account here, and I'm going to click this option called continue, and I'm going to click this option called continue. So it's running the authentication process here. So now it's completed. You can able to see the tick mark here, and the next step, we're going to click this option called code. So here we're going to basically begin to create an interactive geemap and display it. So to do that, I'm going to mention as geemap equals to, and I'm going to mention as geemap dot map. So it automatically pops up here, and inside the function, and here I'm going to mention as base map equals to satellite, and I'm going to mention comma here, and I'm going to mention initialize Earth Engine. So I'm going to click this particular one here, it automatically pops, and here I'm going to mention this so it's equals to false, and let me remove this particular one here. We already mentioned outside here, and here I'm going to mention as geemap, and I'm going to run this code here. So it's going to give us an interactive map here. So right now we can able to see the base map here, and we have a set of options that is available. We have this layer called S3 World Imagery, and this is our base map here, S3 World Imagery. You can able to see that, and we have a set of options here. For example, I'm going to navigate here, and I'm going to click this option. And for example, I'm going to enter a specific study area here. So for example, let me enter this particular study area. So I'm going to click enter to search, and it gave me a set of results here. You can able to see here, and let me add a L to it, and let's click enter again, and now it gave me a result here. So we're going to navigate this to this particular location here. So you can able to see this particular river here. So we can identify the river turbidity for this particular area. So to select this particular region of interest, what's gonna do is I'm gonna navigate another option here, and we have set of options here. For example, we can draw a line or a polygon or a point here. So in my case, I'm gonna draw a polygon. So I'm gonna select this particular option, and I'm gonna draw over this particular area here. So right now I can able to see I've selected my region of interest here. So in the next step, what I'm gonna do is I'm gonna click this option code. So what we're gonna do is we're gonna capture the lost drawn feature on the interactive map as our region of interest. So we have already drawn our region of interest here. You can able to see, and to capture the last drawn feature on our interactive map, to fix it as our region of interest. So I'm gonna mention the study area, and so let me give some space to it, and gonna mention as geemap, and it automatically pop up here called draw lost feature. So I'm gonna select tab here. I'm gonna accept this, and I'm gonna mention dot geometry. So basically the geemap keeps track of this drawing interactions. So the draw lost feature refers to the most recent feature. So we have drawn here, which refers to this particular one we have drawn, and it's going to refer the draw lost feature. And what we're going to do is we're going to mention study area, similar to the Earth Engine JavaScript. So I'm going to click this option called to run this code here. So it ran the code and it gave us this particular output here, the polygon with 5 vertices and the coordinates. So these are the following set of coordinates we created in our region of interest. You can able to see from this interactive map here. So in the next step, we're gonna create a function to compute NDTI. So to do that, I'm gonna click this code here. So we're going to define a per image processing function. So a function to compute and mask NDTI. So for that, I'm going to mention this definition. So now we're going to declare a function named NDTI that takes the Earth Engine image as an input. So to do that, I'm going to mention def, and I'm going to mention this compute. So I'm going to mention this compute NDTI image. So now we declared a function named compute NDTI, so that it's going to take the Earth Engine image as an input here. And the next step, in this step we're going to do is cloud probability band from our linked cloud collection. So here I'm going to mention this cloud prob equals to, I'm going to mention this image dot select the probability. So I'm going to accept this particular one using tab. And the next step, we're going to define another variable called low cloud mask equals to, so let me make some changes here. Low cloud mask variable equals to, so here I'm going to mention this cloud prob, that is probability. I'm going to mention is less than 20. So in the next step, we're going to apply some scaling factor to our Sentinel-2A Imagery. So let me show you this particular one here. So this is harmonized Sentinel-2 MSI multispectral instrument level 2A. SR as a represents surface reflectance, and the dataset availability is from 2017 to 2025, and the dataset provider is European Union ESA Copernicus. And using this particular code, we can access this data here. So now we're going to navigate to the band sections here. So in the band section, we have this particular scale value called, you can able to see the scale value, which is similar to all the bands. So we're going to apply the scaling factor. This value is around 0.0001. So we're going to apply this particular scaling factor. So what we're going to do is we're going to mention SR, that is surface reflectance, equals to image. So we're going to mention this image dot select, and I'm gonna mention is band so b dot star. So we're gonna mention this particular one, and now we're gonna apply the scaling factor. So I'm gonna mention this particular function called multiply, and I'm gonna mention the value here, that is 0.0001. Let me verify the value here, which is 0.001. So it is correct. So once we apply the scaling factor, the next step, we're going to compute the normalized difference water index as well as the normalized difference, the turbidity index. So this is the formula to compute NDWY, which is the NDWY is equals to green band minus NIR divided by the green band plus NIR to compute normalized difference water index. So to do that, first I'm going to mention is NDWY equals to, so here I'm going to mention is SR dot normalized difference so we're going to mention the bracket here, and here I'm going to mention the band B4 and B3. So we're going to mention band B4, and B3, and here I'm going to mention is B3. So it automatically pop-ups here. So anyway, I'm going to mention this B3. And now here I'm going to mention dot rename NDWY, and I'm going to create another variable called NDWY, or let me create another variable called water mask equals to, so I'm going to mention is NDWY dot greater than or equals to 0.1. So we're going to apply a threshold value, so which going to extract all the water areas in our study region. So in the next step, and here I think I've made a mistake in the band here. So to compute normalized difference water index, we have to use B3 and B8. So these are the two bands which is required to compute the normalized difference water index. So basically this is the formula to compute normalized difference water index, that is NDWY equal to green minus NIR divided by green plus NIR. So the B3 refers to green band. So the purpose of this particular indices is used to detect the surface water bodies, and it enhances the water features while suppressing the vegetation and soil signals. So let me get back to Google Colab. So now to compute the normalized difference turbidity index, we're going to mention NDTI. NDTI equals to, so what I'm going to do is I'm going to mention is SR dot normalized difference, and here I'm going to mention the bands here. So here I mentioned the bands like B4 and B3. So the formula is B4 minus B3 divided by B4 plus B3. So it's going to give us the normalized difference turbidity index. And next is we're going to rename as a dot rename NDTI. So the next steps, we're going to apply the cloud and water mask and keep the original time property here. So to do that, so we're going to mention a new variable here, that is NDTI masked equals to. So here I'm going to mention is NDTI dot update mask. And inside this update mask function, what I'm going to do is I'm going to mention low cloud mask, referring to this particular variable we have defined earlier, so you can able to see that. And similarly, we're going to mention update mask to water mask those areas. So in our study region, so we're going to mention is water mask here. And in the next step, to keep the original time properties, I'm going to mention is copy properties. So I'm going to mention is image And here I'm going to mention this system time start. So I'm going to mention this system time start. So to keep our original time property, and last I'm going to mention is return NDTI masked. So let us run this code here. So I'm going to click this option. So now I have rectified the error here. So let me run this code again here. So now the code ran here. You can able to see the tick mark. So in the next step, I'm going to click this option code. So in this step, we're going to build our Sentinel-2A image collection and link the cloud probability. And we're going to filter it using our region of interest and with a suitable time period. And last, we're going to apply the function here. So first step to access the Sentinel-2A imagery, I'm going to mention is S2 TC equals to. So now we're going to access our Sentinel-2A image collection here. So right now I'm going to copy and paste this particular code here. So you can able to see this particular code. I'm going to copy and paste it here. So here I have mentioned as Earth Engine dot image collection Copernicus S2 SR harmonized, and next I've mentioned dot link collection Earth Engine dot image collection Copernicus S2 cloud probability comma probability. So this basically links the cloud probability collection to our Sentinel-2A surface reflectance collection. So this attaches a corresponding crowd probability image as an auxiliary bands under the name probability for each surface reflectance image, so that when you call Insight to compute the NDTI, it finds the band and linking is preferable to joining by the ID in many cases. So in the next step, we're going to filter it based on our region of interest. So we're going to mention dot. I'm going to mention this dot filter bound. And here I'm going to mention this tab to select this particular one. And similarly, in the next step, to filter it based on a specific time period for analysis. So I've mentioned dot filter date 2023 and till gonna mention till 2025. And last, to apply the function we created earlier for this particular one here, you can able to see. So I'm gonna mention this compute NDTI. So here I'm gonna mention this dot map function, and inside I'm gonna mention this particular variable called you can able to see compute NDTI. So I'm gonna mention is compute NDTI. So once you selected your image and applied the filter bound function to select your region of interest, and after applying the suitable time period, and last we applied the function here. So let us visualize, let us see the details of this particular imagery. So here I'm going to mention is S2 TC, and let me run this code here. So here you can able to see we in the output we have the image collection SR S2 SR harmonized. We have a total of 584 elements. So I'm gonna click this. So here you can able to see the features here. So I'm gonna select features. So inside the feature I'm gonna select image here. So you can able to see the band NDTI, and similarly in this particular one the bands we have NDTI, the float data type, and the coordinate reference system. So now let me close this. So in the next step, we're going to convert the Earth Engine image collection to an X-ray dataset using X-ray and Earth Engine. So we're going to use the X-ray open dataset with Earth Engine to convert the Earth Engine image collection S2 TC into an X-ray dataset. So this pulls a pixel value from the server into memory as a labeled array with the coordinates like time, lat, and longitude. So now to do that, first we're going to mention XR ds equals to, we're going to mention XR So we're going to mention xr dot open dataset. So starting with the, we're going to mention the image, that is SR S2TS. So we're going to mention the S2TS, comma, and the engine is equals to GE. We're going to add a comma here. And next to the coordinate reference system equals to EPSG 4326. It is a coordinate reference system. And the scale value, so we're going to mention the scale value to be 0.001, which is 10 meters of resolution. And the last is the geometry. So geometry, we have defined our region of interest as our study area. So we're going to mention the study area. So the geometry is equal to study area here. So in the next step, we're going to ensure the time is sorted and force using the numeric type if needed. So to do that, we can again mention is xr ds equals to. So we're going to mention is xr ds dot sort by. So let me mention xr ds dot sort by. Time. So we're going to mention the time here. And here the xrds.sort by time, it sorts the dataset along the time coordinate. So the time dimension is in the chronological order. And next is we're going to multiply by 1 here. And we're going to give it some space here. So here we are multiplying by 1 forces a numeric conversion for certain X-ray engine outputs. So in the next step, we're going to do is monthly resampling and take the maximum value in each month per pixel. So basically, we're going to take the maximum the turbidity value in each month. So for that, what we're going to do is going to mention monthly. Monthly ds equals to. So we're going to mention this xr ds dot resample. And inside the resample function, what I'm going to do is I'm going to mention is time equals to m, which represents the month. And I'm going to mention the max function here, max function. And inside, I'm going to mention is time. So you can also use the median function or the mean function. So for me, I'm specifically taking out the maximum turbidity value in the each month. So in the year of our analysis period. So for that, I've mentioned the dot max function. So you can also use your median function or mean function. So it is according to your typical condition. And last, I'm going to mention this monthly ds. Monthly ds. So now what I'm going to do is I'm going to run this code here and let us take a look at this. So it's going to basically resample the tell the X-ray to group the data into a calendar months, and for each group take the pixel wise maximum value across all images in that month, and this produces a one raster per month in which each pixel is the maximum NDTI observed in that month, which is useful to capture the peak turbidity events. So now the code has run here. So you can able to see in the output here, we have xray.dataset. So the dimensions, we have the time, longitude and latitude, and the coordinates you can able to see here. We have the time, longitude and latitude, and the variable we have NDTI, and we have these attributes. So in the next step, what we're going to do is we're going to plot the monthly NDTI maps here. So now to plot the monthly NDTI maps, what we're going to do is we're going to mention monthly ds dot NDTI dot plot function, And here what I'm gonna mention and here I'm gonna mention this x is equals to is long, that is longitude, and similarly the y equals to, it's gonna be the latitude, and the coal is equals to the time. So the coal here, which represents creates a separate column for each month. And the next is gonna mention is robust. Robust is equals to true. So the true robust is equal to true uses a robust quantile based color map scaling to reduce the influence of the outliers. And the next so next is I'm going to mention is the column wrap equals to 6. So the column wrap which indicates a 6 column per row. So I have mentioned as column so the column wrap 6, which represents the most so there are at most 6 panels or 6 columns per row. So it is very useful for the many months here we are using our analysis. So the next is the CMap equals to is the cool warm. So this particular one is the color map choice. So it is diverging centered around the mid values. And next is we're gonna mention is Vmax. So Vmax equals to, so it's equals to 0.2. So this particular one is the Vmax equals to 0.2 caps the upper color scale at 0.2. So this fixes the color scaling for the comparability with other maps for each month. So in the next step what I'm gonna do is so in the next step we're gonna save the plot as a JPEG file here. So to do that I'm gonna mention is plot NDTI dot fig dot save fig, and inside I'm gonna mention is NDTI. Let me mention as NDTI maps dot JPEG and comma the DPI equals to 300 and the B box inches equals to tight. And last I've mentioned is print NDTI maps saved as NDTI maps.jpg. So let me run this code and let us visualize the result here. So here we have a set of errors here. So the error which states that the plot NDTI is not defined. So let me check this out. So yes, I have not defined here. So let me mention as a plot NDTI equals to, and let me run this code again. So the NDTI map saved as NDTI maps.jpg here, and we have our maps generated here, that is normalized difference turbidity index starting from 2023 January. So you can able to see all the NDTI maps here. So we can able to see the color codes here, and you can able to see the image here from 2023 January 31 here to we have February, March, April up to 2024 December 31st. We have all those image here, and this is a scale value for our turbidity values here. So let me show you the turbidity table here for the interpretation purposes. So the NDTI is a proxy for water turbidity. It detects the suspended sediments, muddy water, and increased scattering that occurs in a turbid river conditions. Sediments and turbidity strongly reflect the red wavelength, causing NDTI to increase. So if the NDTI value is lesser than 0, it is clear water, low sediment and low turbidity. If the NDTI value is from 0 to 0.05, it is slightly turbidity, mild sediment presence. And if the value is from 0.05 to 0.15, it indicates it is of turbid water, suspended sediments and runoff influence. And last, if the value is greater than 0.15, it is highly turbid and polluted water, the floods, erosion, sand silt transports, which indicates. So based on this table, you can go through the value here. If your scale starts from the positive 0.20 towards the negative of minus 0.20. So you can able to see from this table here, if the value is a positive value, which indicates from 0 to 0.05, it indicates slightly turbid. And if the value is from 0.05 to 0.15, it is turbid water. And greater than that, it is of highly turbid water. From that, you can able to see in the study region have experienced a high turbidity based on the values here. So if it is greater than 0.15, which clearly indicates that it is of highly turbid water. So from this image here, you can able to see from this the images here, the blue which indicates the low turbid or slightly turbid water areas, from the orange color which indicates the highly turbid. So we can able to see from this image here. So in this particular time period in 2024, that is from January towards the March here, so you can able to see the turbidity of this particular study region is pretty high. You can based on the color. And similarly in the other set of months here, so for example in April, in this particular channel here, it is of lesser turbidity compared to this particular one here. As the months move on, so you can able to see the turbidity of this particular the river course, it's kind of lesser. And again, if it comes to this particular month here in 2024, that is the July and August, you can able to see the August, September and October, it has a high turbidity values clearly observed here. So you can able to see from this image as well as our table here. So you can able to see from this table. So let me get back to our Google Colab here. And now you can also download this particular image. You can navigate to this option called folders. And here you can able to see in the sample data, we have this NDTI maps.jpg. So you're going to click this 3 button symbol and you're going to click this option called download. So now it's going to download the image at 300 dpi. So we're going to click this save and I'm going to take a look at this particular image. So you can able to see we have managed to create our turbidity maps as well as we downloaded it here. So you can able to see that. So now let me close this. Similarly, you can download this particular data as a CSV file too. So to do that, again, I'm going to navigate and click this option called code here. So next, we're going to compute a spatial mean for the monthly NDTI value and save as a CSV file. So to do that, we're going to mention is monthly mean here. We're going to mention monthly. Let me monthly mean equals to. So we're going to mention is monthly ds dot mean. And I'm going to mention is dimensions equals to. First, I'm going to mention is the longitude. And I'm going to mention the latitude now. So the dimensions equals to the latitude and the longitude. And we're going to mention is dot to the data frame function. So basically what we're doing is converting the result into a pandas data frame where the index is the time coordinate and the column corresponds to the variable that is NDTI. And last I'm gonna mention is the monthly mean. Dot to CSV. And here I'm gonna mention is the turbidity maps dot CSV, and last I'm gonna mention is print. I'm gonna mention is the saved turbidity map.csv. So now let us run this code, and it's going to export as a CSV. So the output as a saved turbidity map.csv, and going to navigate this option, and you can able to see here the turbidity map.csv. So you can download using you can click this 3 button options, and you can click download, and it's going to download it. So you can able to see the file name. I'm going to click save to download it, and I'm going to open it. So here you can able to see the time as well as the normalized difference turbidity index values here. So it is mean NDTI value. So it is given here from January 2023 to December 2024. You can able to see this. So let me get back to Google Colab environment. So in this video, I have shown you the river turbidity estimation using Sentinel-2A Imagery using Google Colab. So thanks for watching, and make sure that you subscribe to our channel and give us a like.